Hey everybody, you might have noticed that we've been doing some complex math lately. Now, we have to be a little bit careful with complex math because, as you may have realized by now, real things are always real. They are not, in fact, imaginary. And so when we use complex numbers, we're dealing with something that's not particularly real. It's just a useful representation of the information present. So, when you're doing E&M, there are some very particular rules you have to follow when you're going to deal with complex numbers. Okay, so here's a plane wave. This is a purely real plane wave. This is a thing that can actually exist. You may choose to represent it with some sort of complex notation. The very first thing I want to point out is that you have to be a little bit careful about what you're choosing to represent. When you write something like this, that represents cosine and not sine, because if you were to take the real part of it, you would just get cosine back. Now, oftentimes it doesn't really matter if the thing we're dealing with is sine or cosine, but if precision matters, you do have to stop and think about this. If you want to represent sine with a complex exponential, you'll actually have to do something like this. See, if you take the real part of that, you'll just get the sine part. Or if you prefer, you can just use a little phase shift, which is probably the smoothest approach available. Doing something like that would basically be cosine phase shifted, which is in fact sine. There is one other way that you may or may not have seen before. Some people will just write down a complex exponential and then take the real part if they want cosine and the imaginary part if you want sine. And there's nothing wrong with that. Personally, it's not really how I like to do things, but if that's what you're comfortable with, you're more than welcome. Okay, so that's thing number one. It's something we can often ignore. We can just say, oh, well, sine, cosine, who really cares, right? The next thing you have to pay attention to is something that you always have to pay attention to. Let's suppose you have some sort of cosine plane wave, and you want to do math on it. After all, there's really no reason to represent things in complex unless it's to simplify some math somewhere. You can only do certain operations on complex notation without messing things up, at least in E&M. In E&M, you are restricted to only performing linear operations on complex quantities. So operations where you multiply by scalars, add stuff together, stuff like this. If you only perform linear operations on your quantities, you can do that as many times as you want, and then when you're done, take the real part of what remains, and that is the actual field that you have. So here's a little example of a thing you can do with complex representation of fields. You can say, all right, I'm going to start with a little fellow like this. First step, I'm going to change it over into a complex representation. Just a repeat of the above. Now, I am going to use Faraday's law to figure out what the B field associated with this thing is. Okay, so derivatives are linear operators, and so a curl is a linear operator. The curl of this function, which is written in Cartesian, is going to reduce down to, this is the only part that's non-zero. All right, so that's del cross E, which is also equal to minus dB dt. Now I can take the antiderivative of both sides with respect to time, and I'm going to slide that over here. Okay, I know from previous identities that k over omega is 1 over c. And the last step, we're going to take the real part of that and get the actual field. All right, so that's dealing with linear operators in a nutshell. Nice and clean, and it's the sort of thing that, frankly, people can do for a long time before they even realize that there is any sort of special procedure whatsoever. It's only when you have nonlinear stuff that you can really break things. So let me show you how to break things. Okay, so these are the plane wave fields that we recovered before. What we're going to do is we're going to say, hey, what's the pointing vector associated with these things? You need the pointing vector to calculate lots of different stuff, so this is the sort of thing that could happen. And at this point, you have two options. You can either leave it real or switch into complex. But switching into complex is perhaps not such a good idea because a cross product is a non-linear operation. It's taking one field and multiplying it by another field, more or less. And so it's going to break stuff if you do it that way. Let's see what happens if you just leave it real. Alright, so we just have the products of the magnitudes of the vectors up in there. We got k cross j. K cross j is minus I. We take that and fold it in with the other minus sign. We're just going to get an I hat. So we're going to get a pointing vector, which is something like this. And that's what the answer actually is. No ifs, ands, or buts about it. Let's see what would happen if we tried to do this with complex notation. Alright, we cross these little buggers together. We're going to get the product of their magnitudes. Alright, so we mush the magnitudes together. The two exponentials multiplied by one another, that's a thing squared that ends up with a 2 in the exponential. The k cross minus j gives us an I hat again. Now, to back into reality, we'd have to take the real part of this. Ooh, gee, that's kind of bad. What we've done is we've changed the frequency and wavelength of this wave. You see, what nonlinear operators do is they fiddle with the exponent part of a complex exponential. That's the place where the frequency and wavelength information is stored, and you can't just take that and start jamming it together without changing the frequency and wavelength of your wave, which is probably not a thing that you're allowed to do. So now we see firsthand what happens if you use nonlinear operations on complex representations of electric and magnetic fields. There is, however, one place where you can get away with using complex fields and nonlinear operations, and it comes up rather often in E&M. Let's suppose you're looking at some field whose frequency is sufficiently high that you'll never see the time dependence in any realistic situation. This includes basically every optical frequency wave. And when what you want are time averages, you can get to them quickly using complex notation if you're careful. Referring to our example earlier, given some plane wave, the magnitude of the pointing vector will be, and if we time average that, we pick up a factor of a half, and get the usual expression for the average intensity of a plane wave. If you instead represented the E and B fields as complex, and took the magnitude of E cross B star, the exponentials drop out altogether, and what you get is twice the intensity that we got before. Taking thing star thing has a way of doing the time averaging for you up to a factor of 2, if your thing has an essentially sinusoidal form. Thus, in the context of wave optics, you'll often see people finding time-averaged intensities by multiplying things by their complex conjugates and slapping a factor of 1/2 in there. The time-averaged square magnitude of an E field can be written as 1/2 E star E, and the time-averaged intensity of a wave can be written as 1/2 E cross B star over mu naught. So, to sum up, complex is totally okay as long as you either just restrict yourself to linear operations on fields, or take the real part before you perform nonlinear operations, or you're calculating intensities and you use complex conjugates appropriately. And if you ever have any doubt about whether what you're doing is legal, work it out in a pure real form from start to finish and see if you get the same answer.